Happy 2022. Students are super excited to learn some new geometry. So we're just gonna get after it. And the warm-up is a review over, remember how we split 5.1 up into like two sections, like 5.1A, 5.1B, all that good stuff. It's a good review over kind of like both things we talked about. So it's a great warm-up to do together on this day back after our very, very long Christmas break. Okay. Let's start with number 1. If point C is the circumcenter, find each missing value. Who can tell me, raise your hand for this, what a circumcenter is? Ben?
I believe it's it's the middle of all the angles.
It's okay. Tyson?
It's the point equal to all points of the triangle.
Point equal to, okay, I think you have the right idea. Can you be more specific? Oh, Lauren.
From the top of the triangle to the bottom, it's the exact same length.
Okay, you're right. That is one characteristic of this, but what is the circumcenter? Go ahead.
The point of congruency of the three perpendicular bisectors of the triangle.
Try hard.
Wow, that sounded like a definition right out of the notes.
Whoa.
Whoa. Okay, folks, here's what it is. Here's what you need to know. Lauren, you're right about one of the characteristics. It's the point where the three perpendicular bisectors of each side intersect. Okay, so there's lots of lines in this picture. Let me highlight the perpendicular bisectors. Remember, perpendicular bisectors means two things. It means it's perpendicular to each side, meaning one's right angle, and it bisects it, meaning it goes through the midpoint. So this one right here that I just drew from my circumcenter to R, that would be a perpendicular bisector. Okay? Same with C to T, perpendicular bisector. Now these perpendicular bisectors aren't equidistant. There's my third one. But their special characteristic, what Lauren said, is that if I were to draw a straight line from the vertex to the circumcenter, that is equidistant, or they're equidistant from each vertex in the triangle. Okay, so these are all the same. I'm just going to do like a squiggly line because I ran out of hash marks. Those distances are all the same. That's kind of the special characteristics with circumcenters. Okay, so we know all of that because it's a circumcenter. First, they want me to find YC. I'm going to highlight that in green. YC. Based upon what Lauren told us, what would that distance be? 13. Why? Exactly. They're showing me XC right here. They're showing me this is 13. And I know that those are all equidistant from each vertex, so that would also be 13. That's what we did with that little sweet line. That'd be 13. If you want to write it in, you can. Okay. The next one they want me to find is CT. Highlight this one in orange. CT. So if you drew in that right angle, you're able to see this better, that I have a little right triangle here. Everybody see it with this length, this leg of 12. This is what we're trying to find. I'll call it X. And the hypotenuse is 13. So I'm going to have to use Pythag. Okay, remember doing some of these on your homework? So I have to do my two legs. It doesn't matter which leg you put first because we're adding them. So X squared plus 12 squared, but it has to equal your hypotenuse squared. You might recognize this as it's one of like the Pythagorean triples, but if you don't, that's okay. You can solve this out. 13 squared is 169, 12 squared is 144, subtract it over, we get this. X squared is 25. Square root both sides, and we get 5. So CT would be 5. Okay. Everybody good so far? Next one on my list here is YZ. YZ. Oh, that's this one. That's like that whole side of that triangle. So again, since this is the circumcenter, it bisects that side, aka it passes through the midpoint. So if this distance is 12, what would this distance be? 12. So what would that whole side be? 24, exactly. That whole side, YZ, that's going to be 24. Good. Okay, last one. RZ. RZ, this one right here. Well, again, if you drew in the perpendicular bisectors or drew in the right angles, you'll see I have another right triangle. This side's 7. This side's what? 13. Those are all equidistant. I'm going to call this side Y. Well, let's do pi fig again. That Y squared, that my 2 legs squared, has to equal the hypotenuse squared. This one, I want to do 169 minus 49. I don't get a perfect square, sadly. I get 120. That's okay. We can still square root this. We're just going to write it as a simplified radical. So that'd be the square root of 12. Oh, just kidding. Square root of 4. That's a perfect square. Times the square root of 30. So 2 root 30. We've simplified radicals before, so that's nothing new. That's a review. What a good little refresher coming off of a break. Over circumcenter. Okay, Ben was 1 step ahead of me. Next one is an incenter. Okay, Ben, what do you think an incenter is? Exactly. An incenter is the point where all the angle bisectors intersect. So in number 2, it says point P is your angle bisector. Find each missing value. Okay, let's kind of label what that means then. So if it's the angle bisector, that means from the vertex to this point, it's bisecting that angle. So it's splitting it into 2 congruent angles, right? That's what bisect means, splitting it in half. So there's my angle bisector from vertex C, from vertex E. There's my bisector from angle A. There's my bisector. Here's the special characteristics with angle bisectors. If we look at the shortest distance from the incenter, that point, to each side in the triangle, well, we know, first of all, the shortest distance from a point to a line is always the straight perpendicular line, right? So that's what they're showing you here. These aren't perpendicular bisectors. They're just showing you that this distance, which is the shortest, meaning it's perpendicular, this distance from each side of the triangle is always the same. And incenters always lie inside the triangle. Okay, circumcenters can be inside, outside, or on the hypotenuse, depending on what type of triangle it is. But that's kind of the special characteristics with incenter, is that they're equidistant from each side of the triangle. Okay, remember that? All right, so they want me to find BP. Well, based on what I just told you, if they're showing you that this distance, PF, is 3, this is also going to be 3, and so is PD, so that's just going to be 3. All those distances are the same. Next, they want us to find CP. Okay, so again, if you draw in that right angle, this helps you see this better. I'm going to use Y here because I used X later on. If I want to find this distance, I see I have another right triangle here, but this time my unknown is the hypotenuse, right? So this time I'd have to do, you can either start with 3 or 9, doesn't matter. The 2 legs squared added together. They're showing you this distance is 9, equals my hypotenuse squared, which is Y. That's what we're trying to find, or which is CP. All right, 9 squared plus 3 squared is 90. So again, I have something that's not a perfect square. The square root of 90. Perfect square that goes into 90 is 9 times 10. So that simplified radical would be 3 root 10. Okay, I like this next piece because this is actually a review over like the first half of the lesson we did, 5.1a. So it's been a while since we've done this. So what I want you to focus in is this piece right here really quick. Okay, so do you remember doing these problems? And sometimes we use like the converse of this theorem, but like if we knew it was an angle bisector, that means that it's like equidistant from each endpoint of the angle and that these were also equidistant. Or if you knew these were equidistant to the perpendicular distance, then we concluded it was an angle bisector. Do you kind of remember that? That's going to help us find x. So since we know this is an angle bisector because it's an incenter, and we know that the shortest distance, or their equidistance from the two rays that make up this angle, that those are also going to be equidistant. All right, and then we just have this little equation. We got to solve for x. We get 8. Last one. I already have this angle highlighted in yellow. Orange. They want us to find the measure of angle DEF. Well, they told me this little angle right here is 15 degrees. What would this little angle be right here? 15. It's a bisector, splits in half. So what would this whole angle be? 30 degrees. Good. Okay. So that's a review over what we did before Christmas break. It's been a while. What we're going to do today is I'm going to introduce you to two new points of concurrency. This is one where the perpendicular bisectors intersect, circumcenter. This is a second one, incenter, where the angle bisectors intersect. Now we're going to look at medians and altitudes in a triangle, and it's going to be fun. All right. The first one I have for you, one of our new vocab words for today, is an orthocenter. Orthocenter. It is the point of concurrency of the three altitudes. Altitudes of the triangle. If you don't know what an altitude is, here's what it is. It's a perpendicular segment from a vertex to the opposite side or to the line that contains the opposite side. Do you guys remember back in, I don't remember. I think it was chapter 3 where we did those really long problems like right at the end. And I said you have to find the shortest distance from a point to a line. We always talk about how is the line perpendicular, and then I made you like just draw, like sketch in, hey, what would the shortest distance be from this point to this line? And remember I took points off. Matthew, remember that if you didn't draw the right angle?
I have a terrible memory.
Oh, bummer. But remember how like sometimes it had to be like on the outside of the triangle? Yeah, you remember, okay. That's what an altitude is. Or another way to think of it in a triangle is like the height of the triangle. Okay? So these all right here, these are examples of altitudes. That's an altitude from this vertex to the opposite side. From this vertex, if I have like an obtuse triangle, that right there is the altitude. So obviously, these can lie outside the triangle. Okay, look at that altitude, for example. So if I look at the altitudes of each vertice, so let me highlight these quick. So vertex C right here, it's not an angle bisector. Oh, Skylar, are you awake? Oh, couldn't tell me. You're not making eye contact with me. I want to see your face. Oh, good. Okay. From this vertex, the line segment from this vertex that's perpendicular to this side, that's opposite of it, I'll dash that. That's an altitude. From the vertex to the opposite side. From vertex G to the opposite side. There's an altitude. Notice how it's not a perpendicular bisector, right? It's different. It's not bisecting this. It's going from the vertex, perpendicular to opposite side. So where those three altitudes intersect, that's called the orthocenter. And these are all what I drew in red. Those are all altitudes. label more if you want. And then obviously like each point in my triangle, those are all my vertices. So it's like a vertex. Okay, I'm gonna warn you, the next problem is intense. So don't get discouraged because it's probably like the toughest one we're gonna do all day. And I give you a whole page to write work. It kind of reminds me of those one problems we did at the end of chapter 2, at the end of chapter 3, or was it chapter 2? I can't remember. Gosh, I don't remember what we did in chapter 3. What chapter are we in now? 5? Time flies when you're having fun, huh, folks?
Yeah.
All right. So the vertices of triangle HIJ are given here. They want us to find the coordinates of the orthocenter. And with circumcenter, I was a little like lenient of, we can kind of just like estimate it. Now we're going to find exact ones for orthocenter. Okay, so it's just a little bit more steps in the process. Let's start by drawing this triangle. 1, 2, -3, -3, -5, 1. So we have H, I, J. Use a straight edge. Sorry, I'm just on my whiteboard, so I'm being lazy, but use your straight edge to make that triangle. Okay, I'm gonna kind of like write out each step here. So essentially, folks, what we're gonna do, this is why it kind of reminds me of those really long problems, is we're gonna pick 2 vertices. I picked H and I, and we're gonna find the altitudes. So I'm finding the perpendicular line that passes through H and is perpendicular to the line JI. That'd be the altitude to the opposite side. And then we're gonna do the same for the other vertex. We don't really need to find all 3, because if we can at least find where 2 of them intersect, the third one's obviously gonna intersect there as well. Okay? So if you want to write out the steps, you can. You don't have to. You're finding the slope of 2 sides. So you can pick which 2 sides. I picked IJ as one of them, and I picked H as like my vertex. So this altitude is the one with vertex H. So basically, I know that passes through the point 1, 2, and if I can find the slope of IJ, I can find the perpendicular slope, which would give me the altitude, right? So let's go ahead and find the slope of IJ. Slope is change in y over change in x. So here's I and j. So do 1 minus -3. Here's my rise. -5 minus -3. There's my run. Okay, slope, nothing new for us. I get a +4 over a -2. So I get a slope of -2. Does it make sense? Look at that line segment that I get a negative slope. Yeah. If I read it like a book, left to right, it's going downhill. Okay, remember slope, dude? Down. All right. So if that line has a slope of -2, what would the perpendicular line have a slope of? Nice. Positive, opposite, reciprocal, 1/2. So let's just go ahead and draw in this altitude. I'm going to use blue. I know it goes through point H, and I know it has a slope of 1/2. So we can go up 1 over 2, up 1 over 2, or we can go down and left, down and left. Either way, that's giving us a positive sloping line, right? So put a few points on there. Use your straight edge. Does that look like it could be perpendicular to that other side? It should. Okay, if you use a straight edge, it will. But it obviously passes through my vertex H, and it's perpendicular to the other side. We did that using slopes. All right, we're going to find that equation in a second of that blue line. Let's do a second side. So the next one I picked vertex I. You could pick J if you wanted to. So the altitude using a vertex of I would go from point I perpendicular to the opposite side, JH. So let's find the slope of JH. All right, so here I would do change in Y over change in X. Doesn't matter what order you do it in as long as you're consistent. So if I start with H, if I do 2 minus 1, I got to do 1 minus -5. And I get 1/6. Before you go any further, because these problems are really long, see if that makes sense. Does it make sense that I got a positive 1/6 for that green line? It's rising, and that's a slope that's pretty close to 0, so that line's going to be pretty flat, right? Okay, so what would the perpendicular slope be then? -6, opposite reciprocal. Good. So let's take point I. Let's start here at point I, and let's graph a slope of -6. Are you down? 1, 2, 3, 4, 5, 6 over 1. Or I can go up 1, 2, 3, 4, 5, 6, left 1. Take your straight edge. This is obviously a pretty steep negative line. Do my best here. Whew. And it should look perpendicular to the other side. Okay, now when you did circumcenters, I basically just kind of let you like estimate that point where they intersect. So this right here would be my orthocenter. And I don't even need to draw on the third one, right? Because the third one is going to intersect there. If you want to sketch it in, you could. It's going to be something like that. It's going to go through that point. So that right there is my orthocenter, but we're going to find the exact coordinates there. And we're going to do it by finding the equations of those two altitudes, the blue and the orange, and then finding where they intersect. Okay, so that's kind of like my second step then. Step 2 here. Find the equations of the two altitudes. Okay, I'm going to start with the blue one since I started with vertex H. So what I know about the altitude using vertex H is I know it passes through H, which is the order pair 1, 2, and I know the slope. Look at this. I know the slope, we drew that in, is 1/2. Ooh, here's a good throwback problem. Anybody remember how to write equations of a line? Point slope form? Ben?
Y1 minus Y2.
Close. Y minus Y1 equals, keep going, Ben.
M X, or parentheses X minus X1.
Good. Yep. Oh, Miss Hendricks, why do you make us memorize so many formulas? Because they come back. All right. So as a refresher, the X1 and Y1. Oopsie.
Professional.
I don't know what just happened there. My stuff kind of jumped all over the place. Okay, well, this works. You come down. You. Okay. I think it's these things on my shirt. They hit my board. Silly. Okay. The X and Y stay in your equation, but the X1, Y1, that's talking about the point. You guys remember this. So Y1 is 2, X1 is 1, and then the slope is obviously M, like that. And then to write it in slope-intercept form, you just distribute the 1/2 and solve for Y. Hang with me, folks. I know this is the longest problem we're going to do today. And we're not even halfway done. Okay, -1/2 plus 2 is 1.5 or 3/2. So that right there is the equation of that blue altitude. What's the y-intercept of that line? 3 over 2, 1.5. Does that look like my y-intercept right there? That it could be about 1.5? Yeah. Right? Doesn't it look like that's where it crosses my y-axis? So that equation makes sense. find the equation of the orange one. The orange one, vertex I, obviously has the point I, which is -3, -3. And we know the slope is -6 because it's perpendicular to that side JH. So same thing. I'm not going to rewrite out the point slope form. We got to do y minus y1, which is -3, so it ends up being +3, equals mx minus -3 is +3. Distribute. I don't mean to go too fast, guys. This is just review. We did a lot of these problems. I mean, you do them in Algebra 2. Not Algebra 2, Algebra also. I know we've done a lot of them in geometry. Okay. So according to that equation, what's the y-intercept? -21. Does it make sense if I were to keep drawing this, that it's going to cross maybe somewhere down here at -21? Yeah, that looks legit. Okay, so everything makes sense. And these are things, folks, that will save yourself time to check as you're going through it versus doing the whole problem and then looking at the key and you're like, oh, I did it wrong. Where the heck did I go wrong? Like, check as you go. Like, does this make sense that I got a positive slope here? Does this make sense, this equation? Could that fit my line that I drew? All right, so now I have the equation of the blue altitude and the orange altitude. How can I find where they intersect? That's my third step. Any ideas? It's okay if you're wrong. I just want to guess. Alejandro?
Just draw them.
We did that.
Draw the 2 lines that are just found.
We did that. I want to find exactly. I like your thinking. Graphically, we could estimate it. How could I find it algebraically? Exactly. Ben?
You kind of equal each other.
Set the equations equal to each other, or it's a little like substitution even, really. Set these two equal to each other. Figure out when does this line equal this line. When are they the same? All right, so here's my blue equation. When does 1/2 x? Nice job, Ben. Hashtag impressed. Wait, I forgot. You guys don't say hashtag anymore, right? You guys told me that, I think.
That's your generation.
Oh, like as a joke?
Yeah.
Okay. So I was joking. All right, here's my other altitude, the orange one. Now I gotta find where this is where it gives me a little bit of the feels of those other problems we were doing. I'm probably gonna double both sides to get rid of those fractions. You don't have to if you don't want to, but just remember you gotta double everything if you do that. So that'd become x, that'd become 3, that'd become -12, that'd become -42. That to me is a little bit easier to solve. I'm gonna add over the 12x and isolate my variable. Subtract 3, divide by 13. It's not a nice number. 13 is a prime number, so we're going to leave it as that improper fraction. And, Alejandro, I actually like what you said. But would there be any way to tell from a graph that that's exactly where it crosses is at -45/13? I mean, I know you guys are bright, but that would have been really hard to estimate that that's what that x coordinate would be, right? But we're not done because we got to find the actual order pair. But here's what we could do. We could see if our answer makes sense. So take this fraction on your calculator and do it like a division problem. -45 divided by 13. Somebody with a calculator do that for me quick. I think it's like 3 something. -45 divided by 13. Okay, so about -3.5. Now, if you used a straight edge, does it make sense that that x coordinate? Oh, mine's pretty good. It looks like it's about -3.5, right? It should look like that point is somewhere in between -3 and -4. Okay, so that part makes sense. It's also looking like I should get a negative y coordinate. Any ideas of how I can find the y coordinate? Algebraically. Alex? Yeah, plug it into one of the equations. I'd probably use the orange one because it's less fractions. Orange says, hey, y is negative 6x minus 21. It lies on this line. So let's plug it in. We get another kind of nasty fraction. I believe it's negative 3/13. Can someone give me that decimal too? Sorry. We knew we should have got a negative number. Now, don't like rely too much on your graph, because if you don't graph it perfectly, like with a straight edge and everything, it's not going to be exact. But use it as like a reference of like, oh yeah, that could make sense. Someone give me that decimal quick. 3/13, 3 divided by 13. Okay, I'll do it.
0.02.
What'd you get?
0.02.
Okay. Oh, that makes sense, right? Just below 0.02. The good news is, folks, I think all the ones on the homework you get nice whole numbers. Once. Okay. I picked the hard one to do together. All right. That's orthocenter, where the three altitudes intersect. Ready for a new one? This one's nicer. The next and final is the centroid. This is the point of concurrency, so the point of intersection of the three medians of a triangle. What is a median, you may ask? A median, I put this in here for you, is a segment that joins a vertex and the midpoint of the opposite side. So it goes from a vertex to the midpoint of the opposite side. That's a median. So if we look at the median of each side or of each vertex, however you want to think of it, so like this median right here, I'll start over here. I mean, I can label this triangle A, B, C. So from vertex A to their side, passes through the midpoint, so it splits that segment in half, that side in half. From B to the midpoint, splits that segment in half. From C to the midpoint, splits that segment in half. Where those three medians intersect, that's called the centroid. All right, so these are all medians. And then these are obviously still like my vertex, but I would maybe label like this one's like a midpoint. Oh, I know. I almost forgot. There's a kind of a special cool characteristic of a median. And I made a little example to show you during RTI. And I shouldn't say the median, I guess more the centroid. The centroid is the point where the triangle balances. Okay, so I'm going to show you really quick. So I drew this little triangle in RTI, and I just kind of like estimated the medians by taking my ruler and like measuring the distance of each side and then finding the midpoint. And then I took my straight edge and drew the segment from each vertex to the midpoint. Okay, and then I found where they intersected. So if I were to like balance this on the eraser of my pencil, don't blow this. My triangle would balance there. Ah? Isn't that cool? That's what that means. What? The point where the triangle balances is a centroid. Yeah. Okay. Anyways, don't say we never did anything cool in here. That was cool. There's an important special characteristic with centroids. So we have this little centroid theorem. I'll kind of break it down here. So basically it's saying, you know, the medians intersect at a point. We call that the centroid. And the distance has some special characteristics. All right, so if I were to highlight one of the medians, I'm going to highlight AK for a second in green here. So from vertex A to the midpoint of the opposite side here, that'd be K. That's a median. So the segment on the vertex side. So what I mean by that is like from the vertex to the centroid, this segment right here is always 2/3 the distance of the whole median. It's always 2/3. Okay? I don't have a fun like proof to show you guys. It's just a theorem that I'm going to tell you it's true. So 2/3, I'd write this down, is always on the vertex side. Meaning this other segment, so from like the centroid to the midpoint, that's always like 1/3 of that whole distance. Okay, that's what this little theorem is saying. That AP, the one I highlighted in blue, is always 2/3 of the whole median. Let me show you with one other one. If I highlighted this median from B to the midpoint L, this distance right here from the vertex to the centroid, this distance would be 2/3 of that median. And this distance would be 1/3 of that median. Okay, we'll look at a couple examples, but 2/3 is always like on the vertex side. This characteristic holds true for the centroid. All right, here's an example. In triangle XYZ, P is the centroid. So it's where my medians intersect. They're telling me the distance of YB is 12. Find YP and PV. Okay, so let's label what we're given here. YV, this whole median, so it's from vertex Y to this midpoint, that whole distance is 12. First, they want me to find YP, so that's from the vertex side to the centroid, so we're using this little theorem here that I know it's always 2/3 the distance of the whole segment. Well, if the whole segment is 12, what's 2/3 of 12? 8. That distance is 8. Okay, that will hold true. That's like the special characteristic for centroids. Now, next they want us to find PV. We could use a little common sense here. If we know the whole segment's 12, and we know YP is 8, what does PV obviously have to be?
4.
Yeah, I don't know where you got to. 4, right? Or let's use the characteristic, hey, we know PV is 1/3 the whole segment. You could use this knowledge too. What's 1/3 of 12? No. 4. Okay, or as I like to call a little segment addition postulate, that obviously those have to total 12. Okay, let's try one that's a little bit harder. This time, using the same picture, if PU is 6.3, find XP. All right, well, these lie on the same median. So I know this whole median would be XU. So let me ask you this. Would that segment PU be 1/3 or 2/3 of that whole segment? 1/3. It's not on the vertex side, right? So this is 1/3. So what would be a quick, easy way to find XP? Times 2, just double it, right? If this is 1/3 of the whole segment, XP is just going to be double 1/3, aka 2/3. So it's just going to be 12.6. Now, if they asked you to find X, you obviously could just add those together, right? And if you're given like this distance, you could just take half of it, because 1/3 is obviously half of 2/3, right? Okay. I think we have time for one more. This one's similar. Actually, why don't you guys try this problem while I pass out the worksheet, okay? No. The worksheet's due Wednesday. All right, you guys try this next one. It's very similar to the one we just did.
1, and RO, just 2.
Alejandro,
Yes.
please take this seriously. It's important. Okay, for sake of time, LO, this whole median, is 30. So LR would be what of 30? 2/3. It's on the vertex side. What's 2/3 of 30? 20. Okay, using the little segment addition postulate, what does RO have to be? 10, right? Or we know RO is 1/3 of that segment. And 1/3 of 30 is also 10. Okay, we'll stop there. We'll finish these notes tomorrow. The worksheet isn't due till Wednesday, but you should be able to do like most of the problems on the worksheets. The only thing we haven't done is find the exact coordinates of centroids. So give it a try, but we will pick this up tomorrow. Stop recording.